Good afternoon. We are going to start the last session of today, the afternoon session, and the first speaker is Ignasi Mundet Riera, who is going to talk about action in topological manifold. Ignasi.
Okay, so I'm really very happy and very honored to be here and to give a talk in this conference. So thank you very much for the invitation. And I had a great fortune of being a student of Oscar. This was many years ago, more than 20 years ago. I think the first time we met was in a course you gave on cyberwitten theory in Autónoma University. So I remember Carlos was also there. Yeah, I remember we were staying in the Hotel Escuela, which I don't know if it still exists. So we were walking through the forest to go to the lectures. I remember the almond trees in Fuencarral blossomed. It was very nice. And the Sierra with the snow. So I learned a lot in that course, and I learned a lot during my PhD and also a lot afterwards. So I don't have words to appropriately thank so many things I have received, but let's try the conventional formula. So thank you very much. Okay, so in this talk, I'm going to explain some results about finite transformation groups. And well, this is a subject which is not closely related, at least in any way that I know, to most of the subjects that have been the subject of the talks in this conference, although what I'm going to talk about has some relation with Jochen's talk, some relation. But there is indeed at least a formal relation between the result I want to discuss and one result of Oscar. And to explain this, let me explain some pattern that one finds in many rigidity results in geometry. So maybe one typically has a collection of geometric objects, let's call it S, and a functional. And a situation that one encounters in many cases is the following. The functional happens to be, say, bounded above. And the objects which attain the maximum tend to be more rigid or less abundant than those in the other fibers of phi. So let me give a few examples of this general pattern. The first example is a balloon. Oh, what a coincidence. I have a balloon in my pocket. I don't know. So if you want to describe very roughly the situation of a balloon, you can do it in terms of how much air there is inside. And certainly this amount of air is limited. There is an amount of air that if you go beyond, the balloon undergoes a birational and noisy transformation. And now, when you are far from this limit, the balloon is flexible. If you put some air, let me try. Still, it is flexible. But if you put more and more air, well, let's suppose that this is the maximum. I don't want to have bad surprises. Then the balloon becomes rigid. Okay? So this is an example of this phenomenon. So this was the party moment of the talk. Now I'll try to be more serious. There is another example which is related to the one of the balloon, which is a parametric inequality. So you consider curves in the plane of fixed length, and the functional is the area of the region enclosed by the curve. And of course, as you know, this is bounded, and the maximal is attained when the curve is a circle. Okay. A much more sophisticated example is Mostow rigidity, not the way Mostow originally formulated it, but after the work of Besson, Courtois, and Gallot, who realized that you can obtain Mostow rigidity in a situation like this one, where the functional is, in that case, minus the volume entropy. So in that case, if you use the volume entropy, then it is bounded below. And then the fourth example this involves work of Oscar, is a situation where the geometric objects are local systems on a fixed Riemann surface with a structure group UPQ. In that case, one takes as a functional the Toledo invariant, so this is a discrete value, functional, but never mind, or just take the absolute value if you want, and this is bounded above. And when you attain the maximal value, then the moduli space has lower dimension than expected. So this is a manifestation of rigidity. So originally, this result was found by Domingo Toledo and Luis Hernandez, and Steve Bradlow, Oscar, and Peter Gotten reformulated the result in terms of Higgs bundles and obtained many other results. Okay, so to begin with, let me give an example of a rigidity phenomenon that fits this pattern, but for continuous actions of tori on topological manifolds. So let me introduce some notation. X denotes a connected topological manifold. Well, what do I mean by an action of a group G on X? Well, this is simply a morphism from the group G to the homeomorphism group of X. And if G has some topology, you typically require this to be continuous, say, with respect to the compact open topology. You assume X to be compact, and this works very nicely. This is a very typical notation for an action of a group on a space. And an important notion is that of effective action. This corresponds to injective morphisms. Okay, a very standard problem, which in fact lies behind most of what I'm going to talk about, is to describe which groups act effectively on a given topological manifold. Of course, if you drop the condition of effective, then the answer is any group can act, because you can always take phi to be the trivial map. Okay, I will denote by Tm the Pn dimensional torus. T0 will denote the trivial group. Now we can define if the following invariant, the maximal M such that the m-dimensional torus acts on X. Okay, so it's a classical fact that this number A of X cannot be bigger than the dimension of the manifold. Okay, and in fact, if you attain the maximum, namely if A of X is equal to the dimension, then the manifold is homeomorphic to the n dimension to the torus. Okay, so this fits the rigidity pattern. Now the proof, I don't really know who stated and proved this for the first time. It was certainly known in the 30s by Montgomery and Zippin, but probably it's older. With the standard algebraic topology is an exercise, this theorem. So for example, you can use the theorem of invariance of domain. Okay. Okay, so my aim is to find analogs of that statement, but for finite groups. Okay? Not tori, finite groups, finite abelian groups. And for actions of finite abelian groups, there is a very important result of the 60s by Mann and Su, which states the following. You assume that X is a close connected topological manifold. Then the theorem states that there is an upper bound on the rank of these are called the elementary abelian groups that can act effectively on X. Namely, there is R of X such that if for some prime P, Z mod P to the M acts on X, then M cannot be bigger than this R of X. Okay, and of course, the important thing here is that R of X is independent of the prime P. So this looks very much similar to the previous theorem, because you can look at this group as an analog of the torus. It is a cyclic group raised to the m power. But this bound R of X in general is much bigger than the dimension of X. So let's try now to define something more refined. Let's define D of X, so X is still a close connected topological manifold, to be the maximal M for which there exists integers Ri going to infinity, and for each I, an action of Z mod Ri to the M on X, an effective action. Okay, so this denotes an injective morphism. Okay, so let me copy this definition in the Blackboard because I'm going to it will be used in all the talk. So E of X is the maximal M for which there exists an effective action of, put it this way, for arbitrarily large R. Okay, so this is going to be D of X. And the idea is that D of X should be related somehow to A of X. Okay. Well, so initially, this definition seems to involve very particular abelian groups, but it turns out that this number captures information about actions of arbitrary finite abelian groups. Namely, the inequality D of X less or equal than K is equivalent to the existence of a number C, depending only on X, with the property that if you have any finite abelian group A acting effectively on X, then A must have a subgroup of index at most C, which can be generated by K or fewer elements. Okay. Now, one of the ideas behind the questions and results that I'm going to talk about is the fact that these sequences, well, that's a pity that this is covering the title. No problem. I can, oh, fantastic. Yeah, maybe this way is better.
I'm sorry.
Okay, so the idea is that these sequences can be seen, Z mod Ri to the M, with Ri going to infinity. This can be seen somehow as better and better approximations of the M-dimensional torus. Okay, so the meaning of this sentence, of course, depends on what the meaning of approximation is. But let me give you a statement for which this sentence has a concrete and true meaning. So if G is a Lie group, and Lie group means finite dimensional Lie group, with finitely many connected components, then the following two conditions are equivalent. G contains subgroups isomorphic to Z mod R to the M for arbitrary large values of R, and on the other hand, G has a Lie subgroup isomorphic to the n-dimensional torus. Now, this can be used to prove an interesting result involving the analogs of these two invariants in the Keller setting. So suppose that X is a compact Keller manifold, then you can define the holomorphic analogs of A of X and D of X by imposing that the actions are not by homeomorphisms, but by holomorphisms. Okay, so A hol of X is going to be the maximal dimension of tori that can act holomorphically on X. I don't require this morphism to be compatible with any complex structure here. So this is just an injective morphism. And D hol of X is the analog of D of X, but replacing homeo by holomorphism. Okay. Now it turns out that for any compact Keller manifold, A hol of X coincides with D hol of X. There is, of course, a trivial inequality. A hol of X is always less or equal than to D hol of X, because inside the n-dimensional torus, you certainly have all possible groups of this form. Okay, so the non-trivial part of the statement is the reverse inequality. So, for example, this is telling you that if you have a compact Keller manifold that supports holomorphic actions of arbitrarily large finite cyclic groups, then this manifold supports a holomorphic action of the circle. Okay, so how does one prove this? Well, let's denote by omega the homology class of the symplectic form of the Keller manifold, and let's define B omega to be the group of biholomorphism that preserves this omega. Okay. Now, the group of biholomorphisms of X is a complex Lie group, but it can have infinitely many connected components. So a priori, you can't apply the lemma directly. However, it turns out that B omega has finitely many connected components. And then to conclude the proof, you use the lemma of Minkowski. Let me write the statement of this lemma here. The lemma says the following: for any n, there exists some Cn, so that for any finite subgroup gamma of G, L, and Z, the cardinal of gamma does not exceed Cn. Okay, so this is a lemma of Minkowski. And I'm going to use it several times in the talk. So by this lemma of Minkowski, if you take any finite subgroup of the biholomorphism group, there will be a big amount of the elements of this group, in the sense that this intersection will have uniformly bounded index inside gamma, which is going to be contained in B omega. And then you can apply the previous lemma. Okay? Now, what we would like to do is to replace in the previous theorem the biholomorphism group by the homeomorphism group, okay? Which is a topological group, but well, it's not only group, but it's in any possible sense, it's an infinite dimensional group. Okay, and here we have this inequality by the same reason that I said before regarding holomorphic actions. So A of x is always less or equal to D of x, and we may wonder whether the equality between A of x and D of x holds always true, as is the case for holomorphic actions. And the answer is no. So there are examples of closed manifolds for which A of x is equal to 0, and yet D of x is strictly bigger than 0. Okay, so this is mainly a theorem of Capel, Weinberger, and Jan. I wrote my little contribution here, which was to write down the details of the inequality. But I mean, Capel, Weinberger, and Jan knew the inequality. It appears mentioned in a paper of another author with a proof. Okay, so this is a result about continuous actions on topological manifolds, but there are examples, similar examples in the smooth category. In the smooth category, the examples are much simpler. You can take a smooth torus and make connected sum with an exotic sphere, and this connected sum has D of x equal to the dimension of the torus, so it has many finite group actions. But there is a theorem by Bourgelea that says that there is no circle action on that manifold. Yes? Excuse me? Real? Real analytic. I've not thought about it. Yeah, that's a good question. Yeah. I don't know. There are also examples in the category of locally linear actions, but possibly in the real analytic category, maybe there don't exist examples, but I don't know. Okay, but so despite the fact that A of x and D of x are not necessarily the same, one may wonder whether the theorem that I stated regarding A of x also holds true for D of x. Namely, if x is a close connected topological manifold, is D of x necessarily less or equal than the dimension of x? And in case you have equality, is necessarily x homeomorphic to a torus? Well, I ask the questions because I have some hope that the answer is yes. I don't dare to say conjecture because I have some evidence, but it's maybe not extremely strong. Some comments. The first one is that it's quite important to keep in mind that when we define D of x, we consider actions of a sequence of groups, which, by the way, I didn't emphasize, but maybe it's important. When I consider the existence of such effective actions, I don't require any compatibility relation between the actions of different groups. I just assume that infinite groups of this form act effectively on X. Okay, but if you consider one single group, say Z mod R to the M, there is no reason to expect that M is going to be less or equal than the dimension of X, unless R is sufficiently big. And to illustrate this, take into account that for any finite group G, you can find a compact connected surface on which the group G acts. Okay? So you can take Z mod 2022 to the 3. This acts on a freely, in fact, on a compact connected surface. Another comment is that the same question that I am asking can be asked in other contexts. Of course, in the context of holomorphic actions, the answer is yes, because we know that for holomorphic actions, D of x coincides with A of x, and A of x holomorphic certainly, for theory, satisfies the same theorem as A of x. But there are other situations for which whether the question is true or false is much less obvious. For example, one can ask the question for replacing the homeomorphism group by the birational transformation group of an algebraic variety. And in that case, the answer turns out to be yes. And there is a theorem proving this, which says, namely, that if X is a projective variety, the requirement is that the ground field is algebraically closed and of zero characteristic. Then if the group of birational transformations contains subgroups isomorphic to Z mod R to the M for arbitrarily large R, then R is less or equal than 2 times the dimension of X. These 2, of course, account for the fact that the dimension is meant to be the complex dimension if you work with the complex numbers. And in case of equality, X is birational to an abelian variety. Okay, so that's certainly not a trivial theorem, but it the situation for birational transformation groups is much simpler than that of homeomorphism groups, because for birational transformation groups, you have very strong structure results based on the minimal model program. Sorry? Oh, you're right, absolutely. Yes, this should be an M, thank you. Yeah. Okay, so let me state some positive results regarding the question. Let me introduce 2 definitions. And a close connected n-dimensional manifold X is rationally hypertoral if it admits a map of non-zero degree to a torus of the same dimension. Okay, so in particular, so to be able to speak about degree, it has to be orientable. Okay, so of course, Tn is hypertoral, rationally hypertoral, but Tn connected some whatever n-dimensional variety is also rationally hypertoral. And you can also give examples of rationally hypertoral varieties that don't admit any morphism to Tn of degree 1 or minus 1. It's the family of rationally hypertoral manifolds is rich. Now, another a different notion is the following. Let's say that a close connected manifold X of dimension 2D is C-symplectic of Lefschetz type if there is a degree 2 homology class whose dth power is different from 0, and with the property that wedging with, making the cap product with omega to the d minus 1 gives an isomorphism between one-dimensional homology and homology in dimension 2d minus 1. Okay, of course, a typical example of manifolds satisfying this condition are compact Keller manifolds. Okay, so we have the following theorem. If X is a close connected n-dimensional manifold, which is, say, rational hypertoral or C-symplectic of Lefschetz type, then for this manifold, d of x cannot exceed the dimension of x. And furthermore, if d of x is equal to n, then the cohomology of this manifold is isomorphic as a ring to the cohomology of the n-dimensional torus. And if we assume furthermore that the fundamental group of X is virtually solvable, and this means that the type 1 of X has a solvable subgroup of finite index, then X not only has the same cohomology as the torus, but it is homeomorphic to the torus. So my aim in the remaining part of the talk is to explain a little bit the main ideas in the proof of this theorem. But before doing that, let me point out that the invariant d of x can be computed in quite a few examples. For surfaces, it's quite simple. So d is going to be equal to 1 for the two sphere, for the real projective plane, and for the Klein bottle. It's going to be 2 for the two-dimensional torus, and 0 for all other closed surfaces. Okay, so of course this is consistent with the question. We can also compute the invariant for higher dimensional manifolds. For example, if you take Tm times Td connected sum with a manifold Y, which has homology non-isomorphic to the homology of the sphere, then this manifold, by the way, is an example of a rationally hypertorial manifold, and d of x is equal to m. The interest of this example is that here you attained intermediate values for d of x. So we know that for hypertorial manifolds, d of x cannot be bigger than the dimension, and you can in fact arrange things so that you can realize all values. With this example, all values except m-1. But then there is another construction which allows you, in fact, to obtain all possible values. So consider an n-dimensional torus, and the involution that, say, in the first k coordinates, rotates half a circle, and in the remaining coordinates makes an axial reflection. So this is a free involution. The quotient is a topological M manifold, and d of this topological manifold is equal to k, where k is the number of coordinates in which you make the half rotation. Okay. In all these examples, a of x is equal to d of x. Good. So now I'm not going to sketch the proof of the theorem as I wrote down. I will explain the proof of a simplified version of the theorem. A first observation is that the condition that d of x is equal to m is equivalent to at least one of the to both of these two statements being true. No, at least one. No, let me see. Okay, yeah, it's written correctly. If d of x is equal to m, at least one of the two following statements is true. One possibility is that you can find subgroups of homeomorphism of x isomorphic to z mod p to the m for arbitrarily large primes p, and the other possibility is that for some fixed prime p, there exist groups of this form z mod p to the e raised to the m inside the homeomorphism group. Okay, so the theorem whose proof I'm going to sketch considers only the first possibility. Okay, for the second possibility, the proof of the theorem follows a similar strategy, but you need some extra ideas. So what I'm going to explain is the following result. Suppose that x, and I'm also only going to explain the case of C-symplectic manifolds of Lefschetz type. In fact, the case of rationally hypertorial manifolds contains, all ideas of the case of rationally hypertorial manifolds are contained in this case also. So suppose that x is C-symplectic of Lefschetz type, then I also assume that there are effective actions of z mod p to the m on x for arbitrarily large values of p, which is a prime, and then I'm going to prove that the cohomology of x, that m is at most n, and in case m equals to n, then the cohomologies of x and the n-dimensional torus are isomorphic, and if pi 1 of x is virtually solvable, then x is homeomorphic to the torus. Okay, so to begin with, I will explain the proof in the case in which the first Betti number is 0. Okay, and then I will explain how to treat the general case. So a first result is the following. I mean, if x is close connected two-dimensional, if x is C-symplectic, which means that it's close connected two-dimensional and it has a degree 2 cohomology class whose diff power is different from 0, and furthermore, if b1 of x is equal to 0, then for a sufficiently big prime p, any action of z mod p on x has a fixed point. Okay, so to prove this lemma, we proceed in several steps. The first thing is that you can replace omega by an integral cohomology class. So this is very standard. The set of degree 2 cohomology classes whose dth power is different from 0 is an open set inside H2 of X with R coefficients. So as soon as you have an element in that set, you can deform it to an element with rational coefficients, and then you multiply this element by a sufficiently by a suitable integer, and then you convert this into an integral cohomology class. So I call it lambda here. Okay. Now, by Minkowski lemma, the one that I wrote there, if P is big enough, then any action of Z mod P on X induces the trivial action here. Okay. In particular, it fixes lambda. Now the idea is the following: suppose that P is bigger than the constants that than the constant necessary for Minkowski lemma to apply, and also than this constant A, which is the times you have to multiply a generator of the cohomology to obtain lambda to the D. And let us assume that you have an action of G on Z mod P. Now the idea is the following. If you assume that the action is free, then you can identify the quotient, which is going to be a topological manifold, with the Borel construction. So here, this is related to one of the arguments of Jochen. Okay. Now, it turns out that the class lambda, which is an ordinary cohomology class of X, is going to can be extended to the Borel construction, and this you can prove using Serre's spectral sequence. You need to prove the vanishing of two differentials, and one differential is 0 because B1 of X is equal to 0, and the other one, so this vanishes because we're assuming that the first Betti number is 0, and this also vanishes because G in that case is Z mod P. Okay, and now if the action, continuing with the assumption that the action is free, it turns out that and using this identification of the quotient with the Borel construction, it turns out that X, the class lambda, is going to be equal to the pullback of some integral cohomology class here through the projection. And this, of course, contradicts the fact that lambda to the D is A times X, where A is non-zero. Okay, so this way you prove that any action of Z mod P has a fixed point. Now, in our case, we are going to assume that X has an effective action of Z mod P to the M. Any element here is contained in a subgroup isomorphic to Z mod P. So any element of this Z mod P to the M acting on X has a fixed point. But in general, a priori, there is no reason why the fixed points should be the same. But it turns out that there is a very general fact when you consider finite group actions, which is this statement here. If you have any close connected manifold X, and you consider finite group actions with the property that any of the elements of the group has some fixed point, then you can't necessarily affirm that there is a point fixed by all the elements. But there is a point that is fixed but most of the elements. Okay, so there is this constant C, which depends only on X, such that for any action, well, I think you can drop effectively here, but for any effective finite group action on X with the property that any element has a fixed point, there is some subgroup of the group G which has index at most C, that constant, which is abelian. The theorem is stated for arbitrary finite groups, although we are going to use only the abelian part. And there is some point fixed by the entire subgroup H. Okay. So I don't have time to explain the proof of this theorem. It's non-trivial, but it would take some time. Let me just point out two examples and then proceed to apply this theorem to our situation. So one example, consider finite group actions on a closed disk. So we all know that any map from the closed disk to itself has a fixed point. This is Brouwer's fixed point theorem. In particular, if we have an action of a finite group on a closed disk, any element of the group will have some fixed point. Now, the theorem implies that there will be some point in the closed disk which will be fixed, but by a large amount of the elements of the group. Okay, and how large depends only on the dimension of the disk, not on the group. Okay? This result is qualitatively optimal in the following sense. In low dimensions, dimensions 1, 2, and 3, you can prove that any finite group action on the closed disk has a fixed point. But in higher dimensions, there are examples of actions that don't have any fixed point. Okay? So you can't replace C of n by 1 in general. So this is one application. There's another application in symplectic geometry. Namely, if you consider finite group actions on a closed symplectic manifold that factor through the group of Hamiltonian diffeomorphisms. There is a quite important result, which is Arnold's conjecture, which is nowadays a theorem, which says that any Hamiltonian diffeomorphism of a closed symplectic manifold has at least one fixed point. So this implies the following. If there is a constant that depends only on the symplectic manifold, a priori only also depends on the symplectic form, such that for any finite subgroup of the group of Hamiltonian diffeomorphisms, there is an abelian subgroup of index at most C and with a fixed point. Okay, in our case, we are going to use this theorem for abelian groups. So we are sort of going to use only half the theorem. And the consequence is that if X is C-symplectic manifold of Leschetz type, keeping the assumption that B1 of X is equal to 0, then for a sufficiently big prime P, if you have an action of Z mod P to the M on X, then this action is going to have a fixed point, a point fixed by all the elements of the group. Okay, so I mean, here I don't say that there is a point fixed by the entire G. Here I say that there is a point fixed by the entire group. And the reason is that if P is, I mean, if you consider a P group, like Z mod P to the M, any proper subgroup is going to have index at least P. So if you take the prime P bigger than the constant C here, then the theorem applied to P groups tells you that any action of the group will have a fixed point. Okay. So to conclude the proof, we use the following lemma. If you have a topological, a connected n-dimensional topological manifold, and you have an effective action of a finite P group on X, which has at least one fixed point, then that group is necessarily isomorphic to a subgroup of GLNR. Okay. So this is what makes this lemma rather non-trivial is that I'm talking about continuous actions on topological manifolds. In fact, the lemma is not true if you relax the condition of G being a P group. So it's not true in general for arbitrary finite groups. But it's certainly true if you consider smooth actions on those manifolds. In that setting, it's an easy exercise. Now, for odd primes P, if you have a subgroup of GLNR, which is isomorphic to Z mod P to the M, then M is at most n divided by 2. And this is a very, very easy exercise. And in this way, we obtain the following theorem. If X is a C-symplectic manifold of Leschetz type of dimension 2D, well, I'm not using the dimension. Oh, no, yes, I'm using the dimension. If the first Betti number is equal to 0, then D of X, this invariant, is at most little d. Okay, so for theory, it's strictly less than the dimension of X, which is 2 times little d. Okay, so this concludes the proof in the case of P1 equals to 0. Now, in general, one needs to use some arguments dealing with the fundamental group, but these arguments will only refer to abelian covers. So recall that an abelian cover is the following. You take any map from your space X to a torus, and then you pull back the universal cover of the torus. Okay, and this is called an abelian cover. The thing is that if your map goes to T to the K, the abelian covering that I denote by X phi, where phi is the map, this has an induced action of Z mod K, which is a group of deck transformations of this covering. And consequently, the homology of the abelian cover is a module over the group ring of Z to the K, which is of course isomorphic to polynomials in K variables and their inverses. Okay, now one can prove the following theorem. If X is closed, then for any map from X to a torus, the homology of the abelian cover is finitely generated as a module over the group ring of Z to the K. Okay, but in general, it's not finitely generated as a Z module. Okay, so let me give an example. You consider the map that collapses this part of this genus 2 surface, and then you project to one of the factors of the torus. If you consider the abelian cover induced by this composition, then this is going to be a cylinder with infinitely many handles attached to it. Okay. Now the second part of the theorem says that if K, which is the dimension of the torus, exceeds the dimension of X, then the homology of the abelian cover cannot be finitely generated. Okay, so very briefly, the proof of one uses Meyer-Vietoris, so it's very Meyer-Vietoris for homology with coefficients in a local system. That's very standard. For the second part, if you assume that the homology is finitely generated as a Z module, then taking coefficients in Z mod 2 or Z mod 3, whatever finite field, the homology is going to be a finite group. And then the monodromy of this the induced action of Z mod K on the homology with finite coefficients will have a kernel which will be a lattice inside Rk, because it will have finite index inside Z to the K. And then you apply the Serre spectral sequence to this fibration, which is a fibration over the K-dimensional torus with fibers X phi. Okay, and the important thing here is that since lambda acts trivially on homology, the Serre spectral sequence, typically in Serre spectral sequence, you have homology of the base with coefficients in a local system given by the homology of the fiber. But if this local system is trivial, which is the case here, then it's basically a tensor product. Okay, because in this case the base is a torus, so the homology is free. And then the second page of Serre's spectral sequence is a sort of a rectangle like this, and you can, choosing the size of the rectangle appropriately, this element here is going to be different from 0, and of course all differentials are going to vanish, and this element will not be killed by any other element, so this is going to survive. And then this leads to a contradiction with the fact that the homology of X vanishes in dimensions bigger than the dimension of X. Yeah. Okay, now I have 5 minutes. No, I think 5 minutes. Yeah. So maybe instead of following this, I'm going to sketch the end of the proof. Now there is another construction, which is the so-called rotation morphism, which allows to somehow linearize the action of the groups. So I'm assuming that I have an action of groups of this form here. So one can construct a map from this to this, making this diagram commutative. Okay, so rho is going to be a morphism from this group to the this. Let me put k here. So k is the first Betti number of x. Okay, so there's going to be a morphism from this group to the k, and also a map from x from x to the torus. That is going to be homotopically non-trivial, and let me conclude here, and it will turn out that so in general the morphism rho going from here to here will not be injective, because you can bound the size of the image in terms of the dimension of x using using this statement here. Okay, so the situation will be the following: you will have a map from x to the to a torus of dimension b, and b is going to be strictly less than the dimension, at most the dimension of m. Okay, and the group that pi to the m will split. One part of the group will act rotating the torus, and the other part is going to preserve the fibers of this morphism. And by an argument similar to the case b1 equals 0, this the remaining part of these groups, which will be, I mean, this is going to be a subgroup, and this is going to be a quotient, to be precise. It's going to fix a variety here of codimension at least b. Okay, and by the lemma that used also in the case b1 equals 0, this is going to fit inside GL of the dimension of x minus b. And now we have all the ingredients to conclude that m is at most the dimension of x. Okay, because you have rank b in the horizontal direction, and in the vertical direction you have m minus dimension of x minus b divided by 2. Okay, so this proves this inequality. The case of equality only happens when b is equal to the dimension of x, and in that case you can prove that the abelian cover is acyclic. And this implies that the cohomology is the cohomology ring is isomorphic to the cohomology of the torus. And the last statement, which when you assume that the fundamental group is virtually solvable, basically what you have is that the abelian cover is not only acyclic, but it is also simply connected. If it is simply connected, that it is simply connected and acyclic, it is contractible. And this implies that the manifold X is homotopy equivalent to a torus. And then there is a very deep result in surgery theory, which is called the rigidity of topological rigidity of tori, which says that any closed topological manifold homotopy equivalent to a torus is actually homeomorphic to a torus. And this is what is needed to conclude the proof. So sorry, I had to run a little bit at the end, but this is basically all I wanted to say. So, so thank you and happy birthday.
So, any questions?
So, thank you. This is a very speculative question, but this bounds and the rigidity, and linking actually with Johan's tori action that relate to stability and moduli, in some like the example you put of UPQ Higgs bundles, these bounds are obtained from stability, from some stability condition. Can you think that maybe in some of these examples, there is maybe some stability condition lurking around, or alternatively, some bounded cohomology kind of argument to find these bounds, like, you know, like the Milner-Wood bounds?
No, I don't know.
I'm asking because you have an action of a group, and I mean, in some algebraic situation, it may be actually related. It makes sense to talk about stability and so on. So
yeah, there is a part that has been hidden below the carpet, which is that theorem. This theorem. So this theorem, the proof of this theorem, this uses different ingredients. One of them is a construction that I call stability. But so what sort of stability is this, the one involved here? So you consider finite group actions with the property that all stabilizers have big index inside the group. Okay, now roughly speaking, the consequence of this is that if you replace your big group by a slightly smaller group, the set of stabilizers doesn't change that much. And I call this a stability condition for obvious reasons. But it would be very nice to relate this to GIT stability. I mean, but I don't know.
Thank you.
The other question. So let's thank again to Ignasi.